We have learned design and analysis of algorithms. So we know about our big O notation, a tighter upper bound and lower bound, right? Theta, big O, all these we know. Okay. Now, what are the different times of running times? Okay, order of one or order of any constant. It's a constant running time. Okay, and order of log n is a logarithmic time. It is less than order of it is like half n, almost close to, almost half the size of n. Okay, so it's logarithmic time. Then comes so it is in the increasing order of complexity. Then comes the linear time, order of n. Order of n square is quadratic, cubic, and so on. We can see so many things. And order of n power k is polynomial time. And order of k power n, when n goes to the power, this is what we mean by intractable. Intractable or non-polynomial. Why we say it is intractable is as n, the size of the n as it grows. Consider a graph with n nodes. And when you say your algorithm works in k to the power n time complexity, when the graph has thousands and lakhs of nodes, like as we see in our social network contact analysis, say I'm analyzing all your contacts in Facebook. So consider every contact is a node in my graph. So consider the amount of nodes that I'll have. So if my algorithm works in, so even if it is 2 power k, so my algorithm becomes uncontrollable when the size of the nodes increases. So it is like intractable. Okay, so these two are exponential time and n to the power and factorial time. Okay, so these are the common notations that we use. And P, NP, NP hard and NP complete, we'll just see an overview that you might have already studied in EAA, just a quick overview. Now, P is a class of problems that are solvable in polynomial time. Okay, and NP is a class of problems, we'll see it. NP is a class of problems that are not solvable in polynomial time. They are more complex than P, but they can be definitely verified in polynomial time. I can verify. So a Sudoku game, if you give me a Sudoku game with blanks, I cannot, the time complexity with which I can fill the blanks is like order of n square. Obviously, I'll have n cross n matrix if you have. I can, for every cell, you can imagine a loop for I equal to 1 to n. And inside that, obviously, you will have for j equal to 1 to n. So you will have for every cell, you will take all the other n cells and you will consider, right? For n cross n, at least for the grid, 3 cross 3 grid, you will do that. So you will get an n square complexity, and even more than that, for a grid, I am talking about n cross n. When you consider all 3 grids together, vertically, horizontally, then it becomes more intractable, right? But given a Sudoku, blank Sudoku, or a Sudoku with solutions filled, okay, I can verify in polynomial time and I can tell that, okay, this is a correct solution or it's a wrong solution, right? The solving is not possible in polynomial time, but verification, if the solution is correct or not, is definitely possible in polynomial time. So that class of problems is called as NP problems. Okay, and the other two problems are like NP complete and NP hard. NP complete, they are both NP and NP hard. This set of problems that falls in both. They are, so NP, you say like they're at least as hard as P problems, but they are still more complex. So NP hard is the hardest of all. Okay, and we'll see a bit like some more extra details. We'll see each of these 4 classes and we'll quickly wind off. Okay, so problems that can be solved in polynomial time, it could be logarithmic, linear, or quadratic time, or up to O power n, like when you can see the definition over here. C is a constant, order of C into n to the power k. C and k are constants, and k is always less than n. When it is equal to n, then it becomes a factorial complexity. So k is always very much less than n. Okay, so these both are constants, and n is the input size, n is a variable. N is a variable, and c and k are constants. Then we say that it can be solved in polynomial time using a logarithmic, linear, or a quadratic time algorithm. Then we call that problem as a polynomial solvable problem. And all the examples, the prime checking, shortest path algorithm like Distra, Bellman Ford, all these are linear search, binary search, all these are polynomial, uh, having like polynomial time for solving. And the non-polynomial problems are that cannot be solved in a polynomial time. So it could be an exponential or a factorial time. So the representation here is C1 is a constant into K to the power C2. C2 is a constant, but you see the variable in the power. Right? So K is a constant, C1 is a constant, C2 is a constant, N is a variable. So as N becomes more, as N becomes huge, so these are the examples, 2 power N power N, or this. As N grows in size, then this becomes very complex. The classical examples are integer factorization. So given an integer, what are the different factors, and graph isomorphism. So we'll see this later. So graph integer factorization is given an integer and all the factors. But if you are given an integer and if you are given all its factors, you can easily verify that these numbers are factors of 64 or not. So the verification can be easily be done in polynomial time. Okay. So those are the class of NP problems. Okay, the problems must be decision problems with a yes or no answer. They cannot be solved, but they can be verified in polynomial time. That is by a deterministic Turing machine. That is by a deterministic algorithm. There is a deterministic algorithm that can tell me that, okay, this now, these are the factors. These are okay. These are valid factors for this number 64. But give all possible factors of an integer for any arbitrary integer. So that is not solvable in polynomial time. And again, when we come to NP complete problem, this is I can transform. So it is similar to NP. It is in NP actually. So I have a polynomial time algorithm to transform one NP complete problem to another NP complete problem. I can transform one NP complete to another NP complete problem, and this transformation can be done in polynomial time. So this transformation can be done in polynomial time, conversion of one NP complete problem to another NP complete problem that we just did now with undecidability in post correspondence. This process is called as reduction, and the reduction can be done in polynomial time. Okay, it's at least as hard as NP, but it's more hard and complex. So verification can be done, and the transformation also can be done. So verification and transformation is done means they are in this class, right? So they are NP complete. Okay, so these are the different problems: traveling salesman problem, knapsack problem, and graph coloring problem. So how can you color a graph with minimum number of K colors? That is a graph coloring problem. So traveling salesman and knapsack. These are NP complete problems. So what is an NP complete problem? It is still an NP problem. So it is difficult to solve, but it's easier to prove or verify. That is, verify the solution. Okay, that's fine. And still one more property, NP complete problem. One problem can be easily transformed or reduced to another problem in polynomial time. That is also a very significant property. If a problem holds both of these properties, and it should be in both NP class and NP hard class. If it is in both of these, then it is said to be an NP complete problem. And the next problem is NP hard. It is not only hard to solve, but it's hard to verify also. So some of these problems are even undecidable, and in NP complete there are close to some 3,000 or 2,000 problems from theoretical computer science. They keep adding problems to NP complete. And NP hard, some of the problems, the most important thing is like, why can't I say all NP complete to be NP hard is like, there are very, very hard problems that are even undecidable. I cannot even tell if I can construct a Turing machine or if it is computationally solvable or not. I cannot even make that decision. Okay. And one more thing is all NP hard can be reduced to any problem in NP. This reduction is possible, and they are at least as hard as NP. And as we see, this is the intersecting problems of both NP and NP hard. Okay, so the summary is this: both NP and N-complete are verifiable in polynomial time, and NP hard cannot be verified in polynomial time. So if we can just prove that an algorithm cannot be verified in polynomial time, then that's also sufficient to prove that the problem is NP hard. Okay. And again, you can see traveling salesman and graph coloring getting repeated over here. Okay, so it is in both an NP hard and an NP. So we call it also as an NP complete problem. So remember this diagram. Okay, and there are some class of NP hard problems which cannot be verified in polynomial time also. So we saw in the definition. So there are some class of problems that cannot be even verified in polynomial time. So those problems come in this area. They're difficult to even verify them in polynomial time. So those comes in pure NP hard. Okay. And generally this reduction, these are sample reductions. So given a traveling salesman problem, I'll take a satisfiability. We'll see what's the satisfiability problem. I'll take that. This is called a SAT problem, satisfiability problem. And they'll go click and then vertex cover, then so this also we'll see the proof now. Proof by reduction. We'll try to prove. So given a satisfiability problem, how am I able to reduce it to clique decision, then to a vertex cover, then to a Hamiltonian cycle, then to a traveling salesman problem. So if I'm able to do this, this is the first ever, this is the first very early known NP complete problem. So if I'm able to prove this, then I'll be able to prove that this is also of the same class. Okay, so that is what we'll do in reduction. So what is the satisfiability problem is? The satisfiability problem is like I'll be given a binary equation with binary variables like this. Okay, A is equal to naught of x, and with all the binary operations, this x, y, and z are variables. Okay, so I have three variables with me and I have an equation. Okay, and this formula A or this equation A is said to be satisfiable if there exists an assignment of values to x, y, z that makes this to true. So a final answer comes this to true. Okay, so you have to choose the values of x, y, and z accordingly, so that this equation becomes satisfiable. That is, it gives a A. So is there an assignment that is existing that satisfies this property? Okay, so hence you have to check that, you have to construct, let us construct a small state space tree. Okay, so we have 2 power 3. So 2 power 3 combinations to check. So we'll start with, we are having three variables x, y, and z. So we'll start with x equal to 0 and x equal to 1. So under that you'll have y equal to 0 and y equal to 1. And under that you'll have z equal to 0. For everything you'll have z equal to 0, 1, z equal to 0, 1, z equal to 0, 1. So see the branches. Okay, so first here it was x equal to 0 and x equal to 1. So in each of this branch, I'll consider y equal to 0, y equal to 1. So, and again, z equal to 0, z equal to 1 for each of the branches. So we have 2 power 3 combinations, and you can see it is a, n comes in the variable comes in the power. So it becomes intractable. Okay, but given x, y, and z, you can easily verify, you can substitute x, y, and z, and you can verify it, it satisfies to give a true as the answer, right? So verification can be done in polynomial time, whereas solution, finding all possible assignments of x, y, and z cannot be done in polynomial time. So this is one of the earliest NP problems that was known. So taking that, we can derive or reduce to other problems, any problem that we have. Okay. And I think we'll take one problem and we'll try reducing and we'll finish to this. Okay. We'll have an NP complete problem reduction. Okay. So what I'm going to take today is, it's a vertex cover problem. So what is a vertex cover problem? Given a graph P comma E, V is the number of, so if you're given a graph, undirected graph, let us take. Okay, so this V1, V2, V3, V4 are the V, and edges, these are the edges, E1, E2, E3, E4, these are the set of edges. Okay, and K will be a positive integer. Positive integer. So these both are given to you. Okay, given this both. Okay, now what is the, it actually it should be called edge cover. So what is this vertex cover problem is, you should be taking a subset of vertices, v dash of size k. V dash is a subset of v, okay? V dash of size k. Will I be able to construct a subset of vertices of size k? K is given, remember. Will I be able to take a subset of vertices? Say if I'm giving k is equal to 2 here. Will I be able to take a subset of 2 vertices, v dash, such that every edge in E is connected to, it should be connected to some vertex in V dash. This is the vertex cover problem. Actually, it should be something like, it is covering edges actually. It's the vertex coverage problem. Given a size k and the graph G, will I be able, I should take a subset out of this vertices V dash of size k such that every edge in the graph should be connected to some vertex in this V dash. For example, if I take, so I have a graph like this, okay. Let me say this is 0, this is 1, this is 2, and this is 3, okay. Now what is the vertex cover for this of size 1? I can say 3, k is equal to 1. So given this graph and I'm given k is equal to 1, the minimum vertex cover is 3. So from 3 is a subset of V, fine. And from 3, every edge connects to at least one of the vertex in this subset, right? So every vertex connects to 3. So 3 is a vertex cover for this given graph. So given graph and k, you should be able to find this vertex cover of size k. Okay, vertex cover of size k. That is very important. K also is given to you. Okay, so similarly, I take another graph A. Let me consider E. So how do I connect? This will be connected. Let me say this is connected. This is connected. Now, can we construct the vertex cover for this? Let me say even this is connected. I say E since E is connected. So if I consider E, I can cancel out this, this, and this. These all three edges are covered. Now, when I consider B, what happens? This edge is covered. Now, this edge is still not covered, right? Either I should include D or I should include C. So, the minimum vertex cover is with 3 edges. Okay. Okay. So, given k is equal to 3, you can construct. If you are asked to construct with k equal to 2, you cannot construct a minimum vertex cover. So, given this graph and given k is equal to 2, your algorithm should be able to tell that, okay, for this graph, for this k equal to 2, I cannot construct a subset of vertices of the size 2 that has connections to all the edges in the graph. So, that is not possible. Okay. So, I think you're understanding the vertex cover problem. I repeat, we'll take a subset. So, the sizes of the subset is also given. We'll take a subset V dash of the vertices of the graph, the size k, such that every edge in the graph, okay, every edge in the graph is connected to some vertex in this subset. Every edge in the graph, if I take 3, every edge in this graph is connected to 3. Okay. So the subset size is also given. That is a problem. Subset size is also fixed. Okay. So now we are going to, this is a NP. We are going to prove that this vertex cover problem is NP complete. So prove vertex cover problem is NP complete. So that is our aim. We are going to prove that this problem is NP complete. Okay. So NP complete, if I prove that it's both NP and NP hard, I'll be able to what? I'll be able to prove that it is NP complete. So let me first prove that it is NP, that is NP, then we'll go to NP hard. Okay. First I'll prove that it is NP and then I'll go to NP hard. We'll do a quick proof. Okay. Later I'll share the notes. You can read that and you can understand. Now, how do I do a NP? I can say that it is verifiable in polynomial time, but not solvable in polynomial time. Okay, now given a, now so that my subset V dash is given. So given V dash, you should verify that, okay, this is a vertex cover for the graph G. Okay, given V dash and K, you will verify that, okay, this V dash is a vertex cover. Okay, so for that, I can write a very simple algorithm. So I can say for every vertex in V dash, I can have a counter. What I can do is, I can remove all adjacent edges of this vertex. Okay, remove all adjacent edges of vertex from E, like whatever we did in this previous problem. Okay, I just removed all these edges, right, from this total edge set. Okay, and I keep incrementing the counter. Okay, when this is done, when this loop is done, if this counter is equal to K, if I get the subset size, and if I have traversed all the edges, if I have removed all the edges, remove all adjacent edges from E, and so that the set is empty, then I can say that, okay, the solution is vertex cover. Else, it is not. Solution is not a vertex cover. Okay. Now we can see this algorithm is solvable in order of K. You have K vertices in V dash. So that's it. It's solvable in. So this verification can be done in polynomial time. So it is proved that this vertex cover problem is NP. So verification I can do it in polynomial time. So to prove that it is NP hard, what I should do is I should take again reduction problem, take a standard problem and try to reduce it. Okay, so I'll take a clique. Do you know what is a clique in a graph? I think this might be a bit, I'll try my best to make you understand, but please, if you're not able to understand it, play this again or discuss with me again, or just go through the notes that I'll send. I'll send you the notes also, what I have written with hand previously, last time when I took it. I'll send you that notes also. Please see that. So if you understand, okay, so this is just a proof. So some might find it difficult to understand at the first explanation. So a clique in a graph is subset of vertices such that every two vertex in this subset, every two vertices in this subset are adjacent. What we are going to prove is, we know that this finding the clique is NP hard. Okay, finding this clique, they call it clique. They're finding this clique from a graph is NP hard. So what is clique? Clique is finding a subset V dash of vertices such that every two vertices, any two vertices you take from the subset, they should be adjacent to each other. So a subset of such vertices is called as a clique. Okay, finding all possible cliques, all subsets in a graph is NP hard. Finding cliques in a graph is NP hard. It's a standard problem. Okay, it's a standard problem. Now we are going to reduce this clique finding problem to what? To a vertex coverage problem. Then we'll be able to prove that this is NP hard. Okay, so now this clique, for this clique problem, we'll consider G dash, which is a complement of G. What is a complement of G? Say, for example, if this is your graph, okay, G complement will have the same vertices, but will not have these edges, and it will have all the edges that are not in this graph. Whichever way you can connect the nodes by the edges that are not in this graph is a G complement. For example, for this node 1, it is connected to these two. So I'll not have this connection, but I will connect this to this. Okay, similarly, if I take this node, it is connected to these two nodes, but it is not connected to this. So I'll connect it to this. Okay, so similarly, if I take the third node, it is connected to these both, but it's not connected to this. So I'll connect it to this. Fourth node, it is connected to only this. So I'll connect this to both this and this. It's already connected. So this is G dash. Has all the vertices in G, has all the edges that are not in G. Okay, that are not in G. Okay. So the problem of finding if there is a clique of size. So you have to find if there is a clique of size K. You're going to say that finding clique of size K is equivalent to finding a vertex cover of size V minus K modulus V minus K in G dash. So this is the proof that we are going to do. So finding a clique of size K can be reducible to finding a vertex cover of size V minus K in the complement graph. Okay, for that we'll consider a very simple assumption that will help us. So I'm assuming there is a clique. I'm assuming there is a clique of size K. Okay, so there is a clique of size K in my graph. So V dash is that clique. Okay, set of vertices. So modulus of V dash or count of V dash is K. So size of V dash is K. Now pick any edge U comma V from the complement graph. Okay, so V dash is a subset of vertices. So it's a clique. So if you take any two vertices from V dash, they'll be adjacent to each other. That is a clique. Okay, any two vertices you take, they'll be adjacent. Adjacent means they'll have edge between them. Okay, so that is a clique. So now I'll pick any edge UV from G dash. If there is an edge UV in G dash, means U comma V is not connected in the original graph. Am I right? Because G dash is a complement. So U comma V is not connected in G. That means they are not adjacent. If they are not adjacent means, very careful, what that means. Either U or V can be in V minus V dash, but not both. This is a very important thing. If you're understanding this, that's it. So either U or V can be in V minus V dash, but not both. Because if both of them are there, that means they are adjacent. They are not adjacent because we are taking this U comma V edge from the complement graph. So the original graph, they are not connected. So both of them together, they cannot be in the clique, right? So one of them has to be outside the clique. We understand one can be inside the clique, but one of them should be outside the clique. That is a concept. Okay. So if I'm able to do this, then I'm able to conclude that all edges in G dash are connected. They are connected to some vertex in P minus V dash. This is the conclusion. So all edges in our complement graph is connected to some vertex in V minus V dash. Okay, so this is the vertex coverage problem. All edges in a subset should be connected to, okay, so this all edges in a graph, all edges in a graph should be connected to some vertex in a subset, right? So this is a vertex coverage problem that we reduced it from the clique problem, right? So this was a clique problem and we reduced it to get a vertex coverage problem. So since the clique problem is known to be NP hard, vertex coverage problem is also proven to be NP hard. So I have proven that my vertex coverage problem is both NP and NP hard. So I can say that my vertex coverage problem is NP complete as well. Okay. So this is the proof. Okay. So I take a clique problem. I am taking a complement graph. So with a complement graph, I can tell that this U and V cannot go together. So they have to go in separate groups. Either one could be, if one is in the clique, the other should be outside the clique. Right. So when I do that, I can tell that, okay, this is a vertex coverage problem. All edges in the complement graph, they are connected to some vertex outside the clique. Okay, so they are connected to some vertex outside the clique. So this description is similar to the vertex coverage problem, right? V minus V dash is a subset, and I'm saying that V minus V dash is a subset, and I'm saying that all edges in the graph G dash are connected to some vertex in this subset, right? It becomes a vertex coverage problem. So I took a clique problem and I have arrived at a vertex coverage problem. So finding cliques is a NP hard problem. So I proved that this is also an NP hard. So vertex coverage is both in NP and NP hard. So I'm concluding that it is NP complete. Okay.